Hello everyone, welcome back to 3 Deviations. In today's video, I'd like to cover the Lagrange error. Now, the Lagrange error is a method of measuring the accuracy of Taylor series. So fairly similar to how we measured the error of many of the other series that we discussed earlier in this unit, we want to measure the approximation of Taylor series to approximate functions, right? So in theory, we can have approximations of functions that look super crazy with Taylor series, but in most cases, we're only going to use an nth degree Taylor polynomial. We're not going to use the whole series. So we know that f of x can be rewritten as the sum from n equals 0 to infinity of 1 over n factorial f to the n of x minus a, or f to the n of a times x minus a to the nth power. We know that's good, and we know that we can evaluate this infinite series if we need to, but normally we'll only take an nth degree of this, so we'll only take this sum to a certain degree. So I could say that maybe I want a quadratic approximation. So I'll take t sub 2 of x, and this is the sum from n equals 0 to 2 of 1 over n factorial f to the n of a times x minus a, the nth power. And that will give me a quadratic approximation to this function centered about a. Let's say that's a. So the Lagrange error tells me how large my error is between the actual function and the approximation at a certain value. So we can calculate these errors, and we can also use the Lagrange error to verify that a Maclaurin series or a Taylor series is valued at our function for all of the for all x values for the whole radius of convergence. So let's actually go into the definition of this guy. So we're gonna say that if f, the absolute value of the nth plus 1 derivative of x is less than some m on some interval, x minus a is less than or equal to d, so our convergence radius, then we can make the following statement. Then we can say that our functional value versus our nth degree Taylor approximation value is equal to the nth remainder, the absolute value of the nth remainder. And the absolute value of the nth remainder should be less than or equal to the remainder should be less than or equal to m times the absolute value of x minus a to the n plus 1 power over n plus 1 factorial. This is basically saying that the remainder here should be less than the next degree or the next contribution from the Taylor series. All right, so let's actually dive into what this means with an example. We're actually going to make good use of this because we're also going to use this to find some other quantities. So we want to find a Maclaurin series for sine. So the sine function. So something we rarely associate with polynomials are sine curves, but we are going to make a polynomial for the sine curve with an infinite series. All right, let's see how this works. So if you remember, we need to find the sum from n equals 0 to infinity of 1 over n factorial, f to the nth power of 0 times x to the nth power. Okay, so we need to look at the derivatives of sine. So if I take derivatives of sine, I go from sine to cos to negative sine to negative cos to sine again. So there's a cyclic pattern that we have here. So we can take all of these derivatives at 0. So for sine, it's going to be 0. For cosine, it's going to be 1. For negative sine, it's going to be 0. And for negative cosine, it's going to be negative 1. And this pattern repeats as we keep taking derivatives to the nth. So we have our derivatives, and that's really the hard part. Now all we need to do is we need to generate some sort of formula. So if we plug it into this formula, we're going to have some 1 over n factorial contribution. Then we're going to have either some 0, or either going to be multiplying by 0, or we're going to be multiplying by 1, we're going to be multiplying by -1. So we get some sort of alternating system here. So all of the even terms are going to disappear because their contributions are from sine, and of course the sine of 0 is 0. So all we care about is the cosine contributions, because that will actually yield a non-zero term. That's why we get only these odd powers in our Maclaurin series. And of course we're dividing by the nth factorial. So we get sine of x equals x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and minus, and we go dot dot dot. We keep on going just like that over all the odd powers. Now, you may have seen in physics that sometimes a lot of people like to make the approximation that sine of x equals x. Well, what this is doing is this is taking a first order approximation. Here we have sine of x, and here we have x. So for small angles, these are very similar. So you can make that approximation. And it comes from the Taylor series. So in physics, you use the Taylor series a lot, but we're going to discuss that in an applications video later. But anyways, we can generate a general term. Obviously, we see an alternating part here. So we get the sum from n equals 0 to infinity, -1 to the n times x to the 2n plus 1 over 2n plus 1 quantity factorial. Okay, so we have a nice series, but now we want to plug it into the remainder formula. So to plug it in the remainder formula, we need to find that m value. So to find the m value, we need to determine the maximum of any of our derivatives. So our nth derivative of x, and note that we're verifying the nth remainder. We're not verifying like the second remainder or something like that. We're taking the full polynomial. We're verifying that it's usable for all x. So if we take the nth plus 1 derivative of our function, well then it's either going to be plus or minus sine of x or plus or minus cosine of x. And the maximum of any of these functions is going to be 1. So we take the maximum to verify that we're getting the most accurate version. So we get the maximum of the nth plus 1 derivative of f is equal to 1. So thus our m value is equal to 1. So we can plug this into the remainder formula. So we get the remainder, the nth remainder of x is less than or equal to m times x to the n plus 1 over n plus 1 factorial. And of course, then we get then we can set the m equal to 1. We can pull the n plus 1 out. Then we can use the fact that our Maclaurin series for e to the x always converges to take the limit on this. We can also use the squeeze theorem because this is absolute value, so we can squeeze r sub n, and it will tend to 0 for all x. So thus our our Maclaurin series for sine of x is valid for all x. All right, in the next video, we want to discuss how to manipulate Taylor series. We also want to discuss some of the common Taylor series that we have, because there are a few that you need to remember. So we'll go over that in the next video. Thanks for watching.